Damien here from Aerotherm, and today I will be showing you how to do 3D meshing on a check valve. We can see we've got the check valve over here, and we are going to quickly open it up to see what is happening inside. On the very right over here, we've got our inlet flange. This is followed up directly by our valve, which is in a partially open configuration. On the very left over here, we've got the outlet flange of our check valve. And taking a closer look at the valve itself, you can see that there are a lot of components within our CAD which are not typically going to be seen within CFD. For example, we've got nuts and bolts here which are not seen within CFD CAD, and we have got external surfaces of our CAD which are not seen in CFD-Ready Geometry. So, how do we fix these? These are typically fixed using the surface repair tool which is highlighted over here. I've taken the liberty of cleaning this up before the video, and we can see we've got our imported CAD over here, as well as an internal clean CAD geometry over here. If we go to our clean scene, we can see this. So taking a quick look at what is happening over here, we've got our internal weighted volume of our cleaned up CAD geometry. We can see this here is the original check valve, and then the downstream portion and the upstream portions have been extended. This is to allow for our fluid to enter the domain over here on the right, and for a boundary layer to develop before the fluid of the domain hits the check valve. With an overall CAD geometry having been shown, we can now go and prepare this for meshing. To do this, we're going to right click on Valve Internals Clean, select Assign Parts to Regions, create a region for each part on our clean geometry, and create a boundary for each part surface and press Apply. We can close this and we will have our region over here, Valve Internals Clean. If we open this up to our boundaries, we can see we've got our downstream portion, we've got our upstream face over here, we've got our overall external walls, we've got our valve, and then we've got our walls fines and our wall valve fines. And if we look at both of these, we can see that these highlight the more fine and intricate components of our CAD geometry. So now we can go and assign our upstream face over here and change the type and make it a velocity inlet. This changes the color so that it is red, which shows that it is a velocity inlet into our domain. Similarly, taking our downstream face and changing this to a pressure outlet will change the color of it to orange to show that it is a pressure outlet of the domain. We can now go and select right click on Operations, Mesh, Automated Mesh. We're going to select Valve Internals Clean, select Polyhedral Mesher, Prism Layer Mesher, and Surface Remesher. These three meshes on the right here are the most commonly used meshing tools within 3D simulations in STAR-CCM+. We can now go and press OK. If we open up our automated mesh over here, we can see that we've got the three meshes that we selected. We've got our default controls and we've got our custom controls. Opening up our default controls and looking at all of our controls from the top to the bottom shows we've got our base size, target surface size, minimum surface size, curvature and proximity settings, prism layer controls, growth rates, TET sizes, and optimization. Starting off by looking at our base size, a base size of 1 meter has automatically been given to us. How do we know if this is appropriate for our CAD size? Well, we don't. We need to go and measure the size of our CAD geometry to see if it is appropriate. A good way to start off by doing this is to look at our inlet region over here and selecting this ruler tool over here. This helps us to measure the distance, so we can now go and measure the distance of the width of our inlet. This is roughly 0.15 meters wide, which means that this base size of 1 meter for our automated meshing operation is far too large for the size of our geometry. So let's go and find this to a size of 0.15 and see what it gives us. We're going to press on our automated mesh, change our execution mode from serial to parallel. This is going to change our meshing operation from using a single CPU core to multiple CPU cores. And we can right click on automated mesh and say execute surface meshes. It's now going to quickly mesh for us, and we can now go and create a mesh scene to view this. Say apply representation to displayers, select latest surface, and we can see here our mesh. If we take a quick inspection of what is happening here, we can see that our downstream and our upstream mesh has relatively well captured the geometry. But if we look at the actual check valve itself, we can see that our mesh has not so well captured what we wanted to in terms of our geometry. We can see that the finer components of our geometry over here are relatively poorly meshed. But what is happening inside? Let's select our wall over here, right click and press hide, and then take a look at our valve and the final components of our valve and our walls. We can see we've got our valve over here, and we've got a nut over here and a screw, and we can see it's not really so well captured, especially when we go and press right click, apply a representation to displays, and compare it to our geometry. We can see this is quite a difference. So how do we fix this? Well, we're going to do the same thing that we just did with our inlet face. We're going to measure the distance of our valve over here, which is just an arbitrary chosen interior CAD piece. And we are going to measure the width of this. We can see that we've got a width of roughly 0.15, 0.015, and 0.016 meters. And we are going to go and update our base size to make it 0.015 meters. This should help to accurately capture what is happening over here with our valve. So we can now go and say execute surface meshes. Looking at this over here, we can see that this is already much better capturing the valve. We can see that this is a much finer mesh. And we can see that our finer components of our walls and our valve have been better captured. If we right click and say restore all hidden parts, we can now compare the external walls. And we can see that while the meshing of our upstream and our downstream region has changed slightly, it has not changed dramatically, especially when you compare it to our finer region, our finer CAD parts over here, which are much better meshed. However, one might ask, why is this here so finely meshed, but then it transitions to such a large mesh over here? Well, this is because of our target surface size and our minimum surface size. Within our surface measure, we've got our base size of 0.015 meters. Our target surface size is set to be 100% of the base size, which means that further out, where there are regions that don't have curvature and proximity, the surface measure is going to aim to have a cell size of 0.015 meters. We can see this by measuring one of these cells over here. We can see that we've got roughly 0.015 meters. This is slightly smaller, but we can see our edges are 0.015 meters. However, when we go to a region which has got large proximity and large curvature, for example over here, we can see that these cells are much smaller. Measuring this will show us a cell size of 0.0015, 0.001617 meters. This is roughly 10% of our target surface size, as has been dictated by the minimum surface size over here, which says that any parts of our CAD which experience large curvature and large proximity can have smaller cell sizes in order to make sure that the overall CAD geometry is well captured. However, we've still got large transitions over here from our small mesh. So if we take this and we look at how quickly it is transitioning, we can say that we do not have a smooth transition. So we can go to our surface growth rate and try to fix this. By default, the surface growth rate is set to 1.3. So if we change this to user specified and set it to 1.15, we will now allow for a 15% growth rate between different cells. So execute surface mesh, and we can quickly at this remesh to see what effect this has. We can see now that we have gone and set in a smaller growth rate. We've got a slightly better growth over here. And we can now go on to our volume mesh. Say restore all hidden parts to look at our overall walls. And then we can look at the volume controls that we have got over here. We've got our prism layer controls, our volume growth rate, our maximum text size, and the post-mesh optimization. So, what are prism layer controls? Prism layers are anisotropic cells which efficiently resolve fluid boundary layers close to the wall. In turbulence simulations, the turbulence model often determines the required first cell layer height through the wall y plus function. To get an understanding of the wall y plus function, we can open Google, go into Wikipedia, and search up law of the wall. If we scroll down over here, we get to our wall y plus function, which shows that our wall y plus is equal to the first cell layer height multiplied by the shear velocity of the fluid in which we are interested in, and divided by the kinematic viscosity of the fluid that we are using. What does this mean? Well, if we look at the graph on the right, we can see that we've got our dimensionless velocity function and our wall y plus function on our x and our y axes. We can see we've got a series of lines here within our graph, where the blue lines represent numerical models that are often used within CFD, and the red line represents experimental data of our wall y plus and dimensionless velocity of our Newtonian fluids as they form boundary layers along the walls of a surface. So, with our numerical models, we can see that we've got a exponentially increasing numerical blue line over here and a linear blue line over here. This exponentially increasing line represents our low wall y plus numerical model, while the linear line represents our high wall y plus numerical model. If we look at our low wall y plus numerical model, we can see that from 0 to a value of roughly 3, we've got pretty good representation in that our model is able to closely represent experimental results. However, if we look beyond this, we can see that the numerical low wall y plus model starts to deviate significantly from our experimental results when we go higher than this. Similarly speaking, when we look at the wall y plus values of above 30 and lower than 300, we can see that our high wall y plus function is able to closely replicate experimental results. This means that prism layers can either be built to follow low or high wall y plus schemes, which empirical models are able to capture well. This means that the parameters of our prism layers can be matched to physical properties. If we look specifically at this, we can look at the number of our prism layers and the prism layer total thickness, which is able to show how much of the boundary layer is captured. If we are using high wall y plus schemes, we don't need a lot of prism layers, and we can get away with only using 2 prism layers. However, if we are using a low wall y plus scheme, we typically need to start using 10 prism layers or more to get a good representation of a low wall y plus scheme. Similarly, our prism layer total thickness should ideally encompass the entirety of our boundary layer. When we look at our stretching factor, this controls our growth and cell thickness while maintaining a smooth transition from our surface mesh to our volumetric mesh. Finally, when looking at all of the prism layer controls that we see here, we want to create our first layer thickness and select it in such a way so that we can achieve the target wall y plus resulting from the viscosity, shear terms, and the cell height. But how do we make a good initial estimate of prism layer thickness? If we take a look at the image on the right, we can see our upstream cylinder diameter, and we can see that we've got a boundary layer that forms along the edges of the wall. In the center, in the dark blue, we've got our free stream flow. Taking a look at the image on the left, we can see very nicely how the boundary layer forms along the edges of the wall as it moves through our upstream pipe. And we can see our free stream flow in the center of our upstream pipe. We know that our inlet cylinder is a diameter of 0.15 meters, and if we assume a boundary layer thickness of 10% throughout the entirety of our upstream piping configuration, this gives us an overall boundary layer thickness of 0.015 meters. If we divide this by if we multiply this by 0.5, this will give us a prism layer thickness of 0.0075 meters at the bottom of our piping configuration and a boundary layer thickness of 0.0075 meters at the top of our piping configuration. With this in mind, we can now go back to our simulation and put in our prism layer controls. Going to our prism layer total thickness, we can change our size type from relative to base to absolute and put in an absolute size of 0.0075 meters. We can now go and quickly give a volume mesh to see what this gives us. Currently, our configuration is in a tetrahedral configuration. Once this has finished generating a volume mesh, it is going to change to a polyhedral configuration, as we can see over here. But we can only see the outside of our simulation over here, our configuration. So to visualize the inside, we are going to create a new derived part by right-clicking, pressing New, Threshold. We are now going to select centroid, open this up and select Z. Why do we do this? Well, this is because the centroid scalar function looks at the center of every single cell within our overall meshing configuration. We want to take a look at everything that is on the right of our origin when looking at our CAD configuration from this view. If we take a look here, we are on the YZ plane, so therefore we are going to take our extraction mode and make it all above 0. We have already got a mesh scene open, so we are going to change our displayer from no displayer to existing displayer, which goes onto mesh 1 and press create. If we close this and then right click on our walls, we can say hide, and this is going to show us our meshing configuration for our volume mesh. We can see here we've got our prism layers which have developed on the side, and we've got an overall volume mesh. But if we scroll in and take a look over here, these faces are relatively large. Let's take our ruler and measure the size of this. This is 0.018 meters, which is larger than the base size of 0.015 meters that we put in. Why is this? Well, this is because if we open up our meshing settings again, we've got a maximum TET size that is by default set to 10,000%. So in order to fix this to make sure that no cells are larger than our base size, we are going to change this to 100%. Similarly, we can see from our refined areas, our volume cells grow very quickly. So we are going to limit our volume growth rate to 1.1. And now we can now go and remesh our volume mesh. If you take a look at the output window over here, it is showing you everything that is happening within the generation of the volume mesh. And then once an initial volume mesh has been generated, it then goes through an optimization sequence. This is going to give us our new meshing configuration, as we can see over here. So if we take a look at the upstream region, our faces will now all be more or less of the same size of our initial base size input. Taking a look over here, we've got our prism layers which have developed along our valve, and we've got our finer regions before expanding back out. Let's take a quick look. While we are happy with our upstream and downstream prism layers, let's have a look at what is happening in our finer regions. This over here looks like it might be a little bit of an issue. We've got our prism layers over here, and then they collapse over here into nothing. So let's go about fixing this. To fix this, we are going to look at our prism layer controls, and we're going to look at our prism layer reduction percentage. This removes cell layers when the prism layer total thickness is below this value. Currently, it is set to 50% of the prism layer total thickness. Let's look at reducing this down to 20%. Similarly, we want to take our gap fill percentage, which specifies the percentage of the distance between closed surfaces that the prism layer mesher fills with prism cell layers. Once again, looking over here, we've got no prism cells, so we want to increase this gap fill percentage from 25% to 40%. Finally, we want to take our minimum thickness percentage, which retracts the cell layer to 0 when the prism layer total thickness is below this value, and reduce this from 10% to 5%. Let's quickly go and mesh this again. We should not see any major differences within our upstream and our downstream regions, but we will see differences in our finer regions. Taking a quick look over here, we can see that we've got prism layers that have developed, but they are not quite to the quality that we want. So let's take a look at putting in some custom controls on our finer regions. Select New, Custom Control, Surface Control. Opening this up, we can look at putting in a part surface, and let's start off by putting in a valve surface control. Opening this up and renaming this to valve. We can open up our controls and change our target surface size to custom. Values, target surface size, and let's make a target surface size of 75% of our base value. Similarly, let's go and create one for our valve fines. rename valve_fines, select walls valve fines, open this up, and let's create a custom target surface size of 35%. Finally, we are going to create a surface control for our fine segments of our walls. Open this up, select wall_fines, open up our controls, put in a target surface size of 50%. Similarly, we want to look at putting in prism layer controls for our wall valve fines and our wall fines. We are going to reduce the prism layer total thickness of these two components down to 40% and see what effect this has. So opening up our wall fines and selecting our prism layers, we can now go and select custom and customize total thickness. Looking at this, we can now select absolute and we can make it 0.006. This is roughly 40% of our base size, and this is smaller than our original prism layer thickness of 0.0075 meters. Similarly, we are going to put this in for valve fines, open up our controls, look at prism layers, custom, customize total thickness, change our prism layer total thickness to absolute and put in 0.006 meters. Now we can go and remesh this to see what result it gives us. Zooming back in, we will be able to soon see our new revised mesh. It's just finishing off its optimization, and there we go. Looking at this new mesh in our finer part, we can see we've now got two sets of prism layers on both sides, as well as our polyhedral cells in between. The polyhedral cells are slightly flat, but for the sake of this video, which is purely just giving you illustrative reasoning, it should be fine. This brings us to the end of our volume meshing. We can see that we've got a mesh that is not too bad and can be used for an initial analysis. However, it is important to always remember that if you are using a mesh for any academic or industrial purposes, it is important to always do a grid convergence study. Thank you very much. This has been Damien from Aerotherm.